Hey everyone, my name is Sandipani. I work as a principal engineer at Nextgen Healthcare. Also, I am the user lead and regional mentor for data platform gigs. And my area of specialization is into data processing and data pipelining, database designing, data modeling, query optimization, and performance tuning. I'm also do lots of things in AI and machine learning from last 3 years, and also I speak at various conferences, including SQL Bits, and data platform geeks events, Azure boot camps, and then any kind of local user group meetings. And this is my third appearance in SQL Bits. So welcome to everyone to SQL Bits 2020. And today's my topic is feature engineering. Let's discuss about it. So what are the different things are there we'll discuss today on this topic. This is one of the very interesting topic, and I would like to explain on the feature engineering more in detail in my presentation. So let's move to the presentation. So today's agenda we are going to cover today is about what is feature engineering and where it is like how it is important, and in the data science life cycle where it comes sorry, what are the different feature types and what are the different characteristics, and what the problem happens with these features, and how we handle those different feature problems. And those are the techniques we are going to talk about today, and we'll have a demo on at the end. So it comes, this feature engineering comes at the very initial phase of our data science project. So if you look at the data is scattered across your application or across your organization, or from it the data can come from various sources. So the data is not in the right form to work with for data modeling or machine learning. So first, most challenging part is for the data acquisition. Once the data is acquired, so we need to look at those data in different formats. So the data first we need to make it in a common format first, and then we do some kind of pre-processing, some kind of different kind of pre-processing or feature engineering techniques we apply based on the data and based on the problem, and then we do the modeling. So in most model data science application, we start with lots of data and care more on the prediction and then explanation. So when I'm talking about your explanation, so and even if you see if I highlighted it, so any problem, the better you explain, it is better for the other side to understand. And the same thing happens here also. So when you have all the raw data, how you represent and how you input the data to your model or to the algorithm, so that the model can understand, the algorithm can understand, and define a better model for us for the prediction. So the explanation is more important. Say for example, suppose I say that I'm not well, but so when I say I'm not well, how do you know that what is not well? So I need to, if I can explain that, okay, yesterday I had a headache, and because I could not able to sleep, and so I had this problem. Well, now you got a little bit of clarity on that. Okay, you could not sleep yesterday, so that's why you're getting headache today. So now if I explain more in detail, hey, yesterday I could not sleep because I had this kind of stuff, or I had the stomach ache, and that's why I could not able to sleep, then it's another area to that explanation of your problem. And that's how you add more clarity to your explanation, and that's way a other person can understand the problem. So in the real world also it happens, we got the most of the raw data from various sources, and then we do the cleaning of the data, and after cleaning of the data, do it is in a one common format. We need to apply different kind of feature engineering techniques to make the data in a proper format, so that a model or the algorithm can accept in, and it can process that data and define a good model for us. Also we need to remember, doing over feature engineering also lead to overfitting. So what is overfitting, what is underfitting? This is not the topic to discuss, but just let me tell you that overfitting means if your model is predicting well in the training data, or if it performs well in training data, but when it comes to test data, if it is not performing well, that's actually called as overfitting problem. In data science life cycle, let's see where this feature engineering comes, what stage this comes. As I said, it comes at the very early stage of the feature engineering. If you see here, very early stage of your data science project. So if you see, once you understand the business problem, then based on the business problem, we start recording or the start acquisition of the data. And the data can come from various sources. It might be a raw file, or it may be a web scraping, or it may data come from NoSQL, or maybe RDBMS system, or maybe a data warehouse system. So based on the problem, you first acquire the data. Once the acquisition happens, the data is not readily available for the modeling. So first we need to do what? Based on the collected data, we need to do different kind of feature engineering. So based on the problem, so the different techniques are transform, binning, temporal, text, images, feature selection. So all different things covers under feature engineering. So we'll discuss more about feature engineering in this topic. And then once the feature engineering happens, the data is ready for the modeling, to train the models, and that we apply those data input to the algorithm, and then the model will be built based on based on the data. And then we evaluate the model. We look at the performance of the model, and if the performance is accepted, then we deploy it to the production. So again, if you look at the whole workflow, so we got the data, then we ingest the data, or we do different kind of ETL transformation to get the data, all gather the data at one place, and then we apply the feature engineering, and then we do the model engineering. Model engineering is nothing but applying the feature data, or applying all the different features. We try different kind of models based on our problem, and then we look at which model is performing well after evaluation. And then once the evaluation happens, once we do the evaluation based on the performance, whichever the model is performing well, we'll deploy to the production. That's how the workflow is. Most time consuming data science task is this data gathering, data pre-processing, doing the feature engineering, so the data is will be in the right format, so it can be utilized for the to train the model. So here in most projects, 80% of the time, almost 80%, not exactly 80%, but almost 80% means 75 to 80 or 75, depends on the problem, and all the data science spend time. If you look at cleaning and organizing data is taking 60% of the time, and collecting data takes 19% of the time, and altogether this phase of is called as actually feature engineering after data acquisition. So the terminology of feature engineering is used by different people or the different professionals in a different way, but that covers almost all things what we talk about, whether it is feature extraction, feature learning, feature construction, feature selection. So all this comes under that. So transforming the data, the real feature engineering is when you get your raw data, you clean the data. After that, the clean data it cannot directly utilize. Mostly in most of the project, the data is not in the right format, can be utilized for the model building. So we need to do certain kind of feature engineering, and then we build the model. So key thing we need to remember, or not remember, but need to understand that features are the numeric representation of raw data. Model is nothing but a mathematical formula or the mathematical summary of features. So choose the right model and features given data, and task is the real work in data science project to predict to define a predictive modeling. So why this feature engineering is important, and so why people spend more time? Because the feature directly influence the predictive model we use and the result we can achieve. So if you see here, it directly influences your prediction, so your model. So the better you do the feature engineering, your model will perform better. So good features will allow you to use less complex model. So it is not necessary that for every problem you need to address through any kind of deep learning or neural network. A problem can be solved through Naive Bayes model algorithm. A problem can be solved with a simple model or simple algorithm. So it is not necessary to define always a complex model, but if you spend more time on the feature engineering, a model can be simpler and it perform well. And it will perform well in two forms, in two ways. One is that performance wise means the prediction time will be better, and the prediction result will also be better if you spend more time on in your features engineering part. The simpler model is always the target, so that it is always good for the target always to be simpler model and predict better results. So the better features you have, you will have better results. So that make the better features, we do this feature engineering technique. So the first topic on feature engineering is what exactly feature is, what are the different types of features. So feature is nothing but a data type, you can say. So there are widely two types of data or feature types available. One is the numeric data, one is categorical data. Numerical data are discrete and continuous. So discrete data is where the number is fixed, like there is no fraction. So I can say how many number of computer you have at your home, or how many member in your family, how many sessions you are going to attend. So those are the discrete numbers. So those are numerical data. And the other side of the numerical type is the continuous data, where there is a frictional point involved, like the price of your house, or temperature, or all this, where you get the fractional part. That's called as your continuous data, numerical data. The categorical data is the label data. So label data are two types. One is nominal and one is ordinal. So nominal is nothing but where the order doesn't matter. Example, I can talk about your country names, and then country names you can talk about, then talk about your gender and color type. So those comes under nominal data, where the order doesn't matter. And the ordinal type, where the order matters. Example are designations, ranking, like suppose we talk about first class, second class, third class. So here it is the order matters. So these are called as your ordinal data. And there is a special category. Sometimes people take this time data type under categorical data, but you can also talk about it, you can keep it as a separate data. I usually deal with the special data because we treat in a different way this date time feature. So once you get the data you do the cleaning of the data. So how you proceed with this feature engineering? So the first step I talk about, from your data set, first you identify what kind of data it is. It is whether it is a numeric data, if it's a numerical, that is discrete or continuous. If it is a categorical data, it is nominal or ordinal. Once you identify that, then we look into the various characteristics of this particular feature or the variable. Variable is nothing but the same feature, or it's a column in my data in a row, or every row we usually say as an observation. And then we look at what are the different characteristics of a particular variable. One of the variable characteristics is the missing data. Missing data means in one of the row certain column values are missing. So this is one of the characteristics. In case of categorical variables, variable contains string instead of numbers. So if it's in string, then, and we know that the mathematical formula always understand the numeric data. So here the challenge is to how can we convert this categorical data to your numeric data. And again, if it's a numeric, we need to think about if you keep a order, whether the order matters or order doesn't matter. Next is your linear modeling assumptions. So do the variable fulfill the assumptions what you think about? The like linear model assumptions are, is there any collinearity between two variables? So there are, like in linear model, which is not the topic in today's discussion, so I'm not going to talk more about it. But yes, you need to find out what are the assumptions you talk about, what model you're going to design. And then the distribution of the data. Distribution of that particular variable is whether it is normally distributed, it is left skewed, it is right skewed, or how the data is really distributed. That also need to look at that characteristics of that particular variable. Then another characteristics is outliers. Certain variables has some different kind of outliers. Outliers is nothing but unusual or unexpected values which are like not in a common circumstances comes, or maybe it is a it's a valid value but it is not a commonly available values. Then it comes to the other characteristics of feature magnitude, which is scale of different features. So when you look into the row, the scale also matters because we need to compare two variables. So you cannot compare two variables if both are not in the same scale. So that is also one of the characteristics. So in feature engineering technique, understanding what data type it is, and then understanding what characteristics it is define what you are going to do at the next stage. So as I said, one of the characteristics is your missing data. So missing data, why the missing data is? So we need to understand from where the source data is, and or based on the data set you need to look at and need to find out that why the problem or why the data is missing in this particular data set. So there are three different way a data can be missed. One is missing completely at random, where the probability of missing data on any attribute doesn't depend on any value of attribute. So you cannot find out any relationship between the one attribute with the other attribute. Another one is missing at random. The probability of an observation being missing depend only on available information. So if the other variable is there, then only you can predict or find out the probability of other variable is missing or not. And the last one is missing not at random. So you can really find out why this particular value is missing, if something is there in relationship with other attributes. So if that kind of thing is available, that kind of data, missing data, is called missing not at random. Now as you talk about, there are two different data types or feature types. One is numeric data. So what exactly, if you look into your data set, most of the data of numeric type having count or price, percentage, measurement and age, or any other kind of thing you talk about, but these are all numeric data types or all numeric data. And when the data comes to numeric type, the most important thing on a feature of numeric type is the scale. What all these different features are in which scale, and then you need to look at what is the distribution of these features. So these things are important for numeric data. Now how we deal with, so there are different techniques to deal with count. So when you have a, suppose I'm just talking about here the count column, or where you have a column called count, where that count can be anything, your attendance count or any kind count of available, but that's a number field. So one technique we use called binarization. So binarization is a technique where depends when you are going to apply, is depends on the problem. Say for example, suppose your problem where you need in this problem for you it is important to know whether a student is pass or fail. But in your data set there is all subject value, subject marks are also available, but you don't want all those values. You just need to know whether for your problem it is important to know whether a student is pass or fail. So what I can do is I can sum up all the marks and then I decide whether the person is pass or fail. So what I can do, that if a certain threshold crosses, like if your pass mark is 150, so if the pass mark cross 150, I can create another feature and keep the value 1 for that pass, and if it is less than 150 I can assign 0 for the particular row. And that's what it is called as binarization. Another technique called quantization or binning. And the binning is nothing but a bucketing. We mostly use to do age grouping. So I don't need all the ages. So what I can do in this case is I can divide various ages to different buckets, like from 1 to 20 I can give in one bucket, another from 21 to 40 I can give a different bucket. So I assign different buckets to different age range. So basically I create different buckets. So this can be done like it is dynamic, or like a quantile binning, or fixed width binning, we can do that. So next thing is more important when it comes to feature engineering is the normalization and standardization. Normalization is nothing but scaling. So what we do, as I said, two features are different in scale, so you cannot compare. I cannot compare between age and your salary. Salary is in currency scale and age is in a normal scale. So both has to compare both the columns. I need to apply normalization to rescale into the same scale so that I can compare. So that is called as actually normalization. We can use in scikit-learn. We have different functions like min max can be utilized to rescale your values. And the other thing is in feature engineering is standardization. So standardization is mostly deal with your distribution. So transform each feature to normal distribution with a mean of 0 and standard deviation of 1. So that's what we do with our features, and that is called as your standardization. And the function we can use for G-score or standard pre-processing techniques we have in scikit-learn, we can use them to make our data standardized. And it is sensitive to your outliers, because if the outliers comes to your data, if it outlier exists, so your all distribution will change, and if the distribution change, definitely the standard distribution gonna change. So that's what the standardization is. After numerical data, let's look into the categorical data. In categorical data, we have two approaches we very widely use. There are various ways, but these two are very common. One is the level encoding, because as I said, I cannot use the string data for my model evaluation. So what I can do is I can use level encoding to give a order integer. So we have different functions, available function in different packages, which we can use to assign a particular number to a particular string data. Other one is your one-hot encoding or dummy encoding, and this is also important, and this is what we do when the order matters. Say for example, I have data of countries. So suppose I have countries like India, UK and USA. So if I give number 1, 2 and 3, the model may predict based on the value given to that is 1, 2, 3, but here the order doesn't matter, so it may bias. So what we can do is that we can create 3 columns called India, UK and USA, and for that row, whatever the person belongs to, we just need to give 1 and rest of the 2 columns to 0, so that every record has these 3 features, because all this categorical value become a feature in my observation, and I can give value whatever applicable for that particular row. That's where I can avoid giving any kind of biasness by giving any order number to my features. Let's move to a demo now to look at how we do different, what are the different kind of technique we apply in feature engineering. So the first thing, as I said, we are not going to cover about how we collect the data. As I said, we are not going to discuss about how the data collection happens. So we assume that the data we have collected in a common format, and then we are going to do our analysis on it. We will apply different kind of feature engineering techniques. So let's go one by one. So in feature engineering, as I said, once you have the data, first you detect whether you have numerical data or what are the different categorical variables you have. So here I'm going to import this pandas package and this numpy package. Pandas package to deal with the data frame, and the numpy package to do different kind of numerical calculation. And then I'm using matplotlib to design different to plot different plots, and then I'm just waiting just to suppress the warnings. Then on my data set, I just taken this data set from this Titanic data set from Kaggle. So you can download from, this is a very famous data set. You can download from in Google. If you search, you can find it there very easily. So I just load the data, and this is my data. So if you look at, we need to understand every attribute well. So we make sure that you understand all attribute column names. Well, sometimes what happens, we with the assumption we use one particular column, and later we come to know that what we assume that column is not exactly the same or what you are thinking. So we need to first understand every attribute name well. So if you see here, so here we are using SES. One is which is your socio-economic status, so like it is first class, second class or third class or lower class in your ship, in the Titanic ship. And then we have an age field. Then this is, we use SIB. SP is nothing but sibling and spouse, and that is like you have brother, sister, step brother, like that. That column will talk about that. And then we have a parch column. The parch column talks about what are the family relationship you have, like parent or mother, uh, like our father child, or what is the relationship, it will show up there. So let's see, to see this is the data. If you look into the old data here, the passenger ID column, then your sibling and spouse column, and the parch. If you look at, these are all your numeric and discrete data. And if you look at your fare column, it's a numeric data, but it's a continuous column, continuous variable, because it has fraction. And then we have categorical data, which are nominal, type are name, sex, ticket, embarked, and survive, because those are not giving any order, or order is not important how it is presented. So then we have categorical data of P class and the cabin. So cabin, if you look at, these are the categorical ordinal or the order matters. And then these are the different types of, so first we find out what are the different kind of features and what are the different types in that. And let's see what is the size of the data set we have. So we have 891 rows, means observations, and we have 12 columns. And let's see, now look at the info. And if you look at here in this data, we have total, we see that we have 891 observation, but when you see this, each column has some missing values. All rows doesn't have this value present. And also in cabin, we find most of the records are null. And in case of embarked, 889 records has data, and very few records has null value for this particular feature. So now let's do some exploratory data analytics. And if you see the data, if you see here the age 38, most of the passengers were age of 38, almost 75 percentile, so that's a good, like most of them are young. And the max age of a passenger in that ship is 80 years old. And if you look at mean age, like an infant also present, so it's a mean age. And the data, you can look at that how many total records, 891 records. And this is the standard deviation of 14, that looks good. And then let's move to see the how the, as I said, like we covered right now, what are the different kind of data types. Then we look into the characteristics, and one of the characteristics we are targeting right now is missing data. That's why I showed you some of the columns has null value. Now let's see how the data is distributed. So if you see the data here, age columns looks quite normally distributed. And the fare, if you look at, almost all of them are into this category, like it is a third category, where many of them are there in that column feature. And passenger ID, there is no value of this, because every record is unique. It doesn't give you any information about observation. The PC class, we have three classes, first class, then second, and third. Most of the passengers are into third category, because first category is very people, only the rich people can buy the tickets, so it's like almost more than 200. And then sibling and spouse, most of them are traveling alone. If you see 0, none of them having sibling and spouse. And this is the survived and not survived. So not survived numbers is above 500, and survived number is above 300. So this is how the data is distributed. Now, as you know that some records are missing, some features has a null value. So if you look at that, again we find out that age 177 observation has age null, and cabin information 687 rows doesn't have the cabin information, and 2 record doesn't have the embarked information. So again, if I look into the mean, if I find out, if you see it is a 20% of the age is missing, almost 77% of the data is missing for cabin value, and this is almost very 2% of data for embarked is missing. So now let's look at how we deal with missing data. In this data, both the missing value of variable cabin and age were introduced systematically, because if you look at wherever the age is missing, cabin information also missing, so missing data is not at random. because those who survived might be they would have collected the data later, collecting age and Kevin information. So we create a dummy variable that indicates whether the value of the variable Kevin is missing or not. So I'm going to create this a new feature. So this is how this is one of the technique that we are adding, which is important for our prediction. So I'm gonna create Titanic Kevin null, and then so this is the record. So 77 record as I already identified. So we created a Kevin null. So if it is a null, we assign 1, and if it is not, we assign 0. And then if I group by with the data what we looked at before, so if you see that whoever not survived, almost 87% of the cases the data was missing, and whoever survived, we have 60% of data is missing. So almost we can just assume, or we can conclude that wherever passengers will not survive, we could not collect the data for the Kevin information. Now if you look into the embark data, so we did not find if we do not find any relationship why this data is missing. So we just see that okay, only 2 records has missing values because there is no relationship. If you look at with other data, so we are not finding any relationship. So we can say the missing data completely at random. We don't know what's the reason behind it. Now let's go and start looking into the age column, that how you handle the age column. So the most commonly used technique to handle missing value for numeric data is to find out the mean and just apply that mean, and let's try to do that. So if you see here, I'm trying to create the distribution plot for missing data, and then I impute the missing data based on the mean of the age, and wherever the age is missing, we'll try to fill that column, and we'll see how the data looks like. So if you see, this data was with missing values, and once I apply the imputed value, the complete distribution got changed. So if you see, you need to remember when you are applying mean the column, the distribution is going to change, but that's okay. Then removing the data, rather if you remove the column, then we may miss, or we may there is a chance of missing so much of information for the model. So rather than deleting, it's better to count the mean and apply that. But you see that we will see that how we can address in a different way this column. So I'm going to create a function where it's based on the name. It will return me Mr. or Mrs. based on the name, and we create a different column using this particular function. So now what I do, I create a new column called Titanic title, and I will assign this particular title function to that. So it gives me a record this way. So there are record with name Mr. 517, and Miss with 182 records, Mrs. with 125, Master 40, and others are 27. Now if I draw the box plot, if I say this is the box plot to identify the quantile information as well as the outliers. So we can see Mr. title is cutting outliers, and the some Miss also has some outliers. Master doesn't have, Mrs. doesn't have, and other doesn't have any outliers. Now instead of applying now this is the technique what I said, it's the art of engineering. So there is no straightforward way to deal with missing values. So we need to understand the problem, we need to apply the feature engineering technique. If a age column is missing, and if I identify that okay, I just apply the mean may not be the right value for that particular column. Why? Because suppose a record with master, if you look at here, there is a kid which is whose age is missing, and you find out the average age is coming around, mean is coming around 35. So whenever you see the kid age is missing, you apply 35, which it will completely change the distribution, and that is not the right way to assign the missing value for that particular record. So what if we do that, we as I said, we first based on the name we find out that how many are Mr., how many are Mrs., and if we try to find out the average for each category. For Mrs. we need to find out the mean. For Mr. we need to find out the mean. For Master we need to find out the mean. And for different based on the different title we have our mean. And then when a record has a missing age, we look into the name title, and based on that particular title we find what is the mean. Sorry, instead of mean we are going to use median. So we'll find out the median and we'll apply that particular median to particular row. I'm sorry, I was saying I said mean, but not, you should use median, because remember mean is very sensitive to outliers, so it is always good practice to use median for this kind of situations. But there is no concrete rule. Again, I'm telling, if you do not have outliers and if you already handle the outliers, then you can definitely use mean. So here I'm gonna apply the missing value of different record based on the mean of different category, median of different category. Then let me draw the graph. So if you look at now, this graph looks bit of more normally distributed. Now next moves to your data imputation for missing value for column embarked. So embarked has 2 counts. So what I could do is these 2 records are embarked field NA, value counts index 0. So I just look at what is the maximum value, S, C and Q. I may apply based on the count, whichever is coming more. So we have 2 missing values embarked. Let's impute it with most occurring embarked stations. So we have S has more embarked stations, 644. So we just apply that value to that particular column, index 0. So index 0 is nothing but my S, 644. So I just apply that value to that. And then data imputation for cabin. So if I look at almost 77% of the data is missing, so almost every record data is missing, so I can go ahead and I can drop the column because it is not giving me much information, because I do not have a way to count it. So this is how my data is. Now I go to the another thing is I did not mention in my presentation, but we call it an interaction feature. So what we do, look into the other features, we look at and try to derive another feature. So that's an interaction feature. So I can create a new feature called family size, and here I use sibling and spouse and parts and plus the percentage himself or herself, and then we find out the total family size. So if I look at, data from a table called family size. Okay, this spelling match. So I just add here like 537 are single and they're traveling, and then 161 people are two in the family size, and like that 102 are 3, and like that 11 families are 7 families are going, the family size is 11 for 7 groups, and like that I have this result set of the family size. So now if I look into the family size frequency, so almost all are traveling single, and then very few are traveling with 2 people, very are 4, and if you look at train, that is 11 what we got. It's very few people are traveling with size more than 10. Then dealing with counts. So as you talk about count, we can deal with binarization techniques. So what I do here, so I just look at, I got the family size. Now I need to remember, for me it is important that the person is traveling alone or with family, because if you are traveling with family, the probability of survival is more, because a family person can help each other during this crisis. So I just created each alone column, and based on the size of the family, if it is greater than 1, then I would assign 1 and otherwise 0 to that. And then I'm just gonna I have done out my feature engineering. Then I'm going to create a model out of it using this. So before that I just imported my logistic regression, because I'm gonna use to predict a person is survived or not. So it's either 1 or 0 or 2 false. So for that I'm going to use logistic regression, and I'm using trends test split to split my data into 1730%. ROC AUC score is to validate or to find out the performance of the logistic regression model. So I just import this free, and then let's see my frequency. So if you see, almost all is alone distribution. So if you look at each alone, more than 300, and not alone is more than 500. So almost many people having somebody traveling. And then I split my data with this test size 30 70 30 ratio, 70% training data. Test size is my 30%, and then I'm using wherever age or year is missing, I just apply fill in it and then calculate the value. So here if you see wherever age is filled in, I'm applying 0. I'm not using anything because that's I'll leave up to you guys to apply that and check if you use those counted value how it performed. Then I use logistic regression. I created a model, and then I apply the fit to train my model, and then I'm going to predict max text. So if you look at the accuracy, I got almost 69%, which is not exactly good, but we can improve it. And when you apply this different variables what we have defined and to my model. Thank you for watching.